Good afternoon, members of the CEAB who are looking at the feedback on the report on design. My name is Jason Foster, and this is sort of a video complement to an email feedback that I submitted earlier. As you can see on the left, this presentation is titled Find the Roots of 9x squared minus 16. And it is an engineering design activity, or at least I hope to convince you of this over the next 10 to 15 minutes. Why am I here? I've been working in engineering education for a long time, specifically on cornerstone and capstone design, and I've been recognized for having done a reasonably good job in this regard. So based on my experience as a design educator, I've looked over the report, and this is where the feedback is coming from. So the report has the two motions. I'll be looking at both of these motions in turn, and I am going to start by looking at motion number 1. So criterion 3443 proposed has been through any number of iterations based on the presentation that I heard. However, I will still say that it could use one more pass, and I'll explain the changes I'd like to suggest and the rationale behind them. First change is to remove thoughtful and creative. Everything students hand in needs to be assessed at some way, and assessing thoughtfulness and creativity is quite difficult. Also because as we teach it, there's a whole spectrum of design activities ranging from selection from a set all the way up through radical invention and specifically innovation. Second change is this notion of removing specified needs. Again, two reasons. First is that there's contention as to whether needs or wants is the preferred language in engineering design education. Second, because the way it's written suggests that the requirements or the needs are given to the engineer, not that the engineer seeks them out, interprets them, and engages with their stakeholders. The third, in keeping with this notion of being a little more flexible, is to move generative to after often. There will be non-generative forms of engineering design, specifically selection, but there are some others. And so just moving it to the other side of often allows that flexibility for different types of design education. A little more contentious change, I'd like to suggest removing objectives and constraints and leaving the term requirements. Two reasons. First, requirements I think is generally understood as being a superset that encompasses objectives and constraints, but also can encompass other models of requirements, such as the FOC, Functions, Objectives, Constraints model used in some textbooks. Last but not least, in keeping with that change, switching constraints to requirements, thus allowing us to say, hey, there could also be functions, there could also be objectives associated with these aspects, not simply requirements. So the fundamental thing that I'm proposing is that we want to make things a little easier to assess on educators and on visitors, and also that the definition should avoid, if possible, prescribing a particular model of engineering design or of engineering requirements. And so I think these changes don't lose the spirit of the initial design, the initial definition, subject to the term creative, that I, again, will assert is a little risky, and enable design educators to maintain some flexibility. So when I teach engineering design, the model that I use is this one. It's a very simple 4-part: frame, diverge, converge, represent, understand, come up with ideas, throw ideas away, and then make sure that you're sharing both what you've created and your knowledge in an appropriate way, no specific path and such. Record keeping, however, being critical. So with this as a model of a design, very simple design process, I'm going to go through and continue with this discussion. So if we come back, we can then flip to the next page that speaks to, how does one identify an engineering design problem? I have some concerns about the notion that engineering design is attributable to the problem or to the statement and not to the individual addressing it. That's for a later point in this presentation. For now, this idea of whether we should prescribe a design mindset or promote a design mindset, how we then do that prescription, and who's responsible are 3 questions that need to be asked. Rather than address them directly, I'm going to go through this example of solving a quadratic. So first thing I'm going to do is say, well, we could change that first question slightly. Eliminate size of, because we are trying to avoid sizing, and change is required to should be used, thus prompting the student to exercise judgment. So by changing the question in this way, I've actually lost a word, so I'm a little shorter, and I've opened up completely to a design mentality, or at least I'll assert that I have, depending on whether the students wish to take it up. That will depend on their context, on how they've been taught, and what they believe the expectations are of their instructors. But again, the example for today is solving a quadratic. So the example I'm now going to work through is find the roots of 9x squared minus 16. So in response to seeing this, we all know that there are some students who, and that was just a little blip, there we go. Some students who will just write down the answer, x is plus or minus 4/3, box it up because they've been told to do so, and declare themselves to have completed the problem. And whether it's a good, well, certainly not a design solution, but it's not even a good solution. There's no steps. It's simply one and done. I think most people would accept this is not what we're looking for. But this is what one student did. Another student can come in and decide that they wish to be a little more explicit, and they're going to say, by inspection, it's the difference of two squares, present us the difference. It's a little better, still not a design solution. We don't get a sense of how the student has thought about why they've chosen to do what they've done. This student says we should factor the polynomial, sets up the two factors and solves. Again, we're getting a little more information. It's continuing to improve, still not design. I think we're on the fourth student now. Fourth student comes in using the quadratic formula, does the algebra, manages not to mess up the bookkeeping. My answer is sure, still not design. And last but not least, fifth student, we're just going to set the polynomial equal to 0, manipulate the algebra, and at this point I'm like, okay, I've got 5 students, 5 different solutions, no evidence of design, what's going on? But if we step back to the invisible part of learning, we have at least 3 different techniques, all of which could work. And if I channel my inner student for a moment, the instructor didn't tell me which technique to use, so I'm kind of at a loss. I can maybe infer it from where we are in the textbook. I hope they're all going to get me full marks. But which approach is the most reliable? Which approach is the most generalizable? Which one is going to be auditable? Is my TA going to look at? What's acceptable? And I've got a whole lot of things I've got to decide since the instructor didn't tell me what to do. And especially as we start looking into issues of bias and issues of positionality, which approach is most me? And we're starting to look at this and say, in the minds of our students, this may be a design problem. So what would that look like? Well, first thing we teach in a design activity is you need to set up your context, learning algebra in an undergraduate engineering course. Next part is, who are our stakeholders? We say that there's the student engineer, the peer engineer, the QA engineer, and the supervising engineer, also known as lecturer, classmates, TA, and instructor. There will be others, but those are perhaps the 4 most important ones. Having identified stakeholders, we start looking at objectives, and this is just a subset. As the learner, I want the right answer. I don't want to have to do too much work. I want to not get the wrong answer, or at least manage that risk. My classmates want something they can follow, easy to learn from, and should they do the unthinkable and copy my answer, they want it to be commonly wrong as opposed to uncommonly. Teaching assistant needs it to be comparable to the expected solution, which in this case is tricky because they didn't tell us how to solve it. And the supervising engineer is looking for conceptual understanding and an engineering mentality and some of the more abstract elements of design and engineering education. I have context, I have stakeholders, I have objectives. I've essentially framed a design problem. I now need to diverge. Well, we know there's bi-inspection, quadratic formula, and algebraic manipulation. There's lots more, some of which are graphical, some of which are computational, some of which are formulaic, and again, there's ones not listed here. When we've asked students in first year to do this and come up with these different techniques, they come up with 17 feasible approaches, some of which, honestly, I'd never heard of. So we can come up with a wide set of possible ways to address this problem. 2 down, 1 to go. We now need to converge. And so I've picked a subset arbitrarily. And those of you who are part of design education may recognize this as a pew chart or the start of one. We'll declare a quadratic formula as the baseline standard. It's the thing against which all others will be compared. And it's guaranteed reliability, only works on quadratics. Not a huge number of steps, easy to audit, but people are going to probably look at this and say, this was a grade 7 activity. If we look at what we saw earlier by inspection, well, if it's a known formula, you're lucky. It's reliable, so it's not as good, but it works on all polynomials, not just quadratics. Steps are, kind of sketchy. There really aren't any. And someone's going to be pretty impressed if you memorize all those forms, or they're going to be pretty appalled. Similarly, as engineering is a self-regulating profession with its own norms, these norms may say things like computation is good. It's better than using quadratic formula. Guess and check's a little sketchy, and Wolfram Alpha, well, we can, if it goes wrong, we can at least blame Wolfram Alpha, although that's not really good engineering. And we can complete the rest of this table as well. So now that we've gone this far, we're in a position as a student to make the call. And this, I think, is where the exercise of judgment is so critical. So student may say, look, assuming there's no additional constraints, and there aren't any in the problem as given from my TA and instructor, I'll use quadratic. I like to, my values personally are, it always works, it's guaranteed, and it's not that many steps. So of the choices, I'll use it. However, I'll start using Newton's method because I hear programming is important, and Wolfram Alpha because when I talked to my mom, who's a practicing engineer, she said, we don't do this kind of stuff by hand anymore. We do it using online tools that have been well tested. So I'm now in this interesting situation where I can present my work and say, I've practiced as an engineer, and I'm going to say even more so. These are decisions that students are making tacitly all the time when we don't give them a particular thing to do, a particular approach to follow. We really ask our students, why did you solve it this way? We either tell them how to solve it, or we assume we're going to all go in the same direction. But we never ask them to share. And that, I think, is the critical part if you wish to conceive of things as a design activity. If we go back to representative model of design, we have all three. We have our framing, our understanding with stakeholders' objectives, our divergence of unknown provenance, but we have a good number of things to pick from, and a fairly reasonable, not great, but reasonable convergence approach. So we have the pieces of design here. And if we go back to the proposed criterion 334 or 3443, we have it all. We have decisions, we have mathematics, we have factors such as cultural, is it going to be accepted by my peers? Regulatory, is it something that can be audited? So what's nice about this is criterion 3443 as given speaks only to the process of developing solutions in response to requirements. It doesn't speak to the problem itself. And it really only speaks incidentally about the nature of the requirements, economics, health and safety, and so on. So under 3443, what I just showed, I would assert should be seen of as engineering design. Or to be kind of blunt about it, finding the roots of a quadratic polynomial should, I assert, be seen of as engineering design and legitimate design education, so long as the expectations on the students and the deliverables are in keeping with criterion 3443 and a recognizable process of engineering design. So if we go way back to the document and we abstract up a little bit, the discussion that comes to play is it the nature of the problem or the nature of the approach? And so waxing philosophical for a moment, there's, I think, a tendency to recognize that design happens only in the face of a particular ontology. Or to say that more practically, we or I as the instructor have said, this is a design problem. Student, you will now do design to it. The other way to look at engineering design education is that it's applied epistemology. It's how you choose to understand the problem. So I gave you this problem, this opportunity to find the roots. Now you go and use an engineering design mentality and approach as you work this through. And again, I'll assert that the goal of a design education should be to make sure that our students can choose to bring an engineering design mentality and approach to their work when it's appropriate for them to do so. It's their call. It's not the problem that calls for it itself. It's the student's choice. Or if the instructor says, do design to it, they should do design to it. So from the point of view of the CEAB, I will put on the table that the assessment of whether design has taken place from an outcome point of view or whether design and use are warranted cannot really be done by simply looking at the questions asked. It's by looking at what the students have done and the focus of the assessment. That's the mentality, and that's the challenge, but it's also, I think, the mentality that's appropriate if we're trying to give design instructors the flexibility and students the opportunity to practice exploring where engineering fits, doesn't fit, and how design can be expressed and undertaken in different ways. Or to finish this off, it's engineering design if you ask the students, find the roots of 9x squared minus 16 like an engineer. With that, I'd like to thank you for sticking with me for the last 16 or so minutes. It has been enjoyable for me to present this. Hopefully you got something out of it as well that can contribute to the work being done. If there's anything else I can do or offer, please let me know, and have a good day.